Okay, so what I'm presenting is the work of many people in the lab, especially in this context of the ERC project. And it is the developments in Scipion to extend to tomography and to define workflows in tomography image processing. And I assume that all of you are familiar with tomography, so that I don't have to explain that part. So I will just explain what are the possibilities in Scipion. And Scipion is a platform that allows the execution of workflows, image processing workflows. So a workflow is you take some input that are the till series, for instance, and then you align the till series, and then you make a 3D reconstruction, and then extract the particles, and all these steps they are performed either manually, so you add the steps one by one, or you define a workflow and then the workflow is executed automatically. And Scipion was developed for single particles originally, and we have in the last year we have extended into tomography. And Scipion adds a layer of interoperability, so you may go from one program to the other. So you may make an alignment with IMOD, and then do a 3D reconstruction with Iman, and then extract the particles with Dynamo. And so all these conversions of file formats and conventions of angles, orientations, and all that, they're handled by Scipion. And then you have also a layer of reproducibility and traceability. So you have a recording of everything that you have done for going uh, from the till series to the final structure. And then you have all the steps in between, all the parameters. If you want to repeat anything, you just have to take that step and repeat it again. And as long as the algorithm is not that does not have any random initialization or things like that, the results should be exactly the same. And also, some advantage of having workflows is that you may identify those steps that are particularly slow, or those steps that are not giving optimal results, so that you can further concentrate on them. And here I will show a couple of examples of what we mean by workflows. So one possible workflow would be you have your tomogram that you have obtained from the alignment and reconstruction of a till series, and then you manually pick your particles. Then you align your picked particles with with respect to a reference. Then so you align into a single class, and then you use that single class to do template matching on the tomogram, and then you redo a particle extraction. So you do two particle extractions. A first one with just a few, in quotes, particles to construct a reference, and then re-extract, do a template matching to do a re-extraction. And then in the extraction, you can have several possibilities. Either you keep the orientation of the particle in the cell, and that is the way Dynamo does, or you extract just the position with a kind of random orientation, random because it is randomly oriented in the cell, and then you recover the orientation by alignment, and that is the approach of Eman, ML Tomo in XMIP, or rely on. And once you have recovered the orientation, you may go into a classification of all those particles. And this is a sensible workflow, but there are many other. So for instance, this is a second one that also makes sense. So you define regions of interest, for instance membranes, and then you do an automatic picking in that region, and that automatic picking can use a regular grid in the membrane. So that is the way Dynamo does, or one of the ways that Dynamo can do. Or for instance, you may look for high density regions, and this is the approach of PySec. And then since probably you have picked many particles that are not real particles, but for instance, particularly in the case of a regular grid, so you use the classification as a way to clean your particles, so decide what is really a particle, what is not, and then you do a particle classification. and at this point you would be at the same uh, state as you were in the previous workflow. So you can reach the same point in many different ways, and most of them make sense, and it is only up to the user and up to the particular data set to follow one or the other. So at the end, a workflow is just a concatenation of these kind of steps, and for that you need some software tool to help you in defining those steps. So the structure of Scipion is there is a core that is the workflow engine that is here at the top, and then this core is complemented by plugins, and there are several plugins, and there are two particularly related to tomography that are at the base. One is EMTomo that defines all the classes related to tomography. And the other one is XMIP, that XMIP is very much related to Scipion, and Scipion needs XMIP for many operations. But then you have the specific plugins doing tomography operations. So you may have a plugin calling XMIP, but only for tomography. Or, for instance, we discovered that XMIP2, that was an old version of XMIP, the maximum likelihood classification of tomograms works particularly well. So you can call an old version of XMIP, of EMAN, Dynamo, or whatever, and we will see all the plugins that we have for related to tomography. So all these somehow are based on these two, and these two are the ones that really talk to Scipion. So here is a list of the protocols that you have now. Probably this list is already outdated, but you can see that there are many different steps that you can already do for tomography image processing. So we divide in Scipion the protocols into categories. So the first category is just letting Scipion know that you have some tilt series or some tomogram or coordinates or whatever. So it is importing your previous data into the system. And then depending on where you start, so let's say that you upload a tomogram. So if you upload the tomogram, probably you would go directly to these steps of picking and pre-processing, subtomogram averaging. But if you start from a tilt series, then you would go to the steps more related to tilt series alignment, 3D reconstruction, and CTF correction, CTF estimation, and so on. And this list is not complete. So a project in Scipion looks like that. So the first steps are always this importing of the objects that you have. So here we have started from a tomogram, and you can import several tomograms. And then, for instance, let's say that you are coming from another package, so you already have some set of 3D coordinates. So you can import the set of 3D coordinates, then you can pick new particles, extract the subtomograms from those tomograms, and then you go into another step. So the concept in Scipion is that the output of one step is the input of the next one, and the Scipion will take care, the protocol of in Scipion will take care of the needed conversion. So let's say that you have to change the orientation of some particles to get into the next program, so the plugin will do that for you, and the same at the output. So at the output we understand the convention of the program, and then we convert it back to the convention of Scipion, so that in that way we guarantee the compatibility and the interoperability between different programs. So let's see a bit the plugins that you need to have when or that you can have when dealing with tomographic data. So the first one is EMTomo, that is a kind of very basic plugin that defines the classes and the kind of objects that you can have in Scipion. So you can have tilt series, tomo acquisition that is more related to what was the voltage of the microscope, the pixel size, things like that. Then you can have a tomogram, you can have a subtomogram, a coordinate 3D. And the nice thing is that at the level of packet or at the level of workflow engine, we understand that you have a tomogram. We don't care if it is a tomogram produced by Eman or a tomogram produced by iMod or whatever. And then for the next program, we will convert that object into the representation that that program needs. So all you see in the system are tomograms, and you don't care what are the details that are underneath. And this plugin is also defining the import protocols, a very basic tilt series motion correction, and that can also produce an average of the tilt series. Then you have another plugin that is this Grigoriev lab that provides two tools to estimate the CTF. One is the tilt series CTF fine, and the other one is tilt series GCTF. And once you have estimated the CTF, you may go into iMod. iMod also allows the estimation of the CTF, and then we have here all the iMod tools to align the tilt series and produce a 3D reconstruction. And you can do that in two ways. One is totally interactive, so we call it Tomo, and then you follow all the steps inside the GUI of Itomo. And at the end, when you produce your final structure, your final tomogram, we keep it in the record of the project. Or you can do it in a fully automatic way. So we have chopped the steps in Itomo into small pieces, so that once, let's say that you have 100 tomograms, so you import the 100 tilt series. So you import the 100 tilt series, and then you do a pre-alignment using iMod Xcore, and this pre-alignment is applied on the 100 tomograms tilt series, and then you can do the construct a fiducial model for those tilt series for the 100 of them. And all these steps here on the left, they proceed automatically. What we don't have so far, and we are already working on it, is having sanity check tools, so that it is not only that you have an aligned tilt series. Sometimes the alignment algorithms fail, so that they say that the tilt series is aligned, but actually it is not, or it has still some degree of misalignment. And then having tools that can separate and identify this condition automatically. But you see that you can go either in a fully manual way, so that you have full control of the thing, and for a particular tomogram that you are very much interested in, you may want to go that way. But you can also want into a massive processing, applying these steps to all the tilt series that you have. Then here is a list of the protocols we have, and I realize now that the CTF is not here, and the CTF of iMod is already integrated too. Then we have also in our institute a person, a researcher that is very much well known, is very well known in tomography, that is Jose Jesus Fernandez, and he produces a set of software tools, especially focused on tomogram denoising, tomogram reconstruction, and he also has some algorithm to compensate for bending in the tilt series. So it is not just an affine, just shaking alignment of the tilt series, but also if the tilt series bends, so he can compensate for that and make a better 3D reconstruction. So we have integrated all his tools into Scipion, and particularly the ones of reconstruction. They are very fast and they produce very good results. We have also integrated Nova CTF that corrects for the CTF along the tomogram. So the upper part of the tomogram does not have the same defocus as the lower part of it. So at the same time that you are reconstructing, you are correcting for the CTF, and this is a very good way of correcting for it. And we have also, as one of our own research topics was the determination of resolution. We started in single particles, but then we found a way to extend that concept to tomography, and then you can define for a tomogram which parts have better resolution than others, and then you may decide to take your particles, your 3D coordinates from those regions that have a higher resolution. Then we have in EMAN 2 we have an almost full pipeline, starting from the till series alignment, automatic, and then 3D reconstruction, manual picking of the tomograms, also template matching, picking, then extracting particles from those tomograms, constructing an initial model to start a subtomogram averaging process, then refining that model, just a single class, and now we are working on the multi-reference alignment that is almost done, and the per tilt refinement that is in progress. This is really starting. Then we have added some other tools, like for instance, this one is you have, let's say that you do an automatic template matching on your tomogram, and then the program produces some candidates to particles, but you are only interested in the particles that are on membranes. So these particles, normally these scattered points outside the main region, are most of them are false positives. They might be also particles, but then they normally cluster in some way. So this tool clusters the coordinates, the 3D coordinates, according to their distance. So it defines from this picking, for instance, it defines 4 regions. And in these 4 regions, you see that all these particles are close to each other, all these particles are close to each other, and then you may impose some filter on what cluster you want to analyze, what is the size of the cluster, what is the maximum distance, minimum distance, things like that. And you may also define regions of interest. So we call ImageJ for that. ImageJ is a very well-known program for image processing, especially in light microscopy, and they have a lot of tools that we can benefit from. So for instance, one of the tools is that you may define a region of interest, like this yellow area, and for defining this yellow area, you have very flexible ways of defining. So you can define geometric regions like ellipsoids or squares or lines, or you have a free form drawing, so you manually draw your region in the tomogram. And this is a tomogram, so what we are seeing is a slice. So you may go to another slice, and you are not restricted to go to the immediate next slice. So you can jump 5 slices in between, draw your region again, jump another 5 slices, draw your region again, and then with all these contours, ImageJ is able to interpolate the slices in between and defines a region of interest that is well defined for all the slices. So we capture that output, and we now have a tool that is, it says in progress, but actually it is finished, that is able to relate these clusters that we have defined before with the regions of interest, so that now that you have your regions of interest, you may take all the clusters from a 3D picking that are close to the region of interest you have defined, and then keep only those points. Then at some point within the project, we thought that maybe reusing the tools that we had for single particle might be help for making a rough classification of the 3D subtomograms. So We have a tool that converts the 3D subtomograms, so small boxes, small cubes that you have picked in your tomogram, in your big one, in the big cell, and make some operation to convert it to an image. And this operation can be just a slice, so you can take a central slice, you can decide which slice you want, and a slice in X, Y, or Z direction. Or you may take a range of slices, so you can take a slab of the subtomogram and add it to have a better signal to noise ratio, and then at that point what you have are just projections. So you have a set of 2D images that now you can submit to any of the 2D classification tools that we have for single particles. Then you may select the particles that you think that are the most interesting, make a subset of the 3D subtomograms that have the same identification number. You may see that here for every image we assign an identifier. This identifier is unique throughout the project, so you can construct very easily subsets of particles. Then we have also a tool to apply the transformation matrices that you have found through 3D alignment of the subtomograms or 3D classification. So let's say that you have a particles. Here is we are representing just the central slice so that you can get a glimpse of how the particle looks like. And you have the identifier number and the transformation matrix applied associated to it. So this transformation matrix aligns that particle as it is extracted from the tomogram to the 3D class that it is assigned to. And but the data itself, the subtomogram, is never interpolated. So as long as you keep the subtomogram and the transformation matrix, you have the full information without any interpolation error. But for some operations it is useful to apply the transformation matrix, and then here you have some interpolation error. You have also problems in the corners of the cube, but some particular programs benefit from having these particles aligned. So you have the possibility to apply the transformation, and then that is no more any transformation, because the transformation is identity in that case. You may recompute a new transformation at that point. So if now you submit these interpolated subtomograms, you submit them to a 3D classification process again, you would estimate a new transformation matrix. So you have this possibility, or you may work all the time with the just extracted subtomograms and the transformation matrices. Then we have a map back protocol. So let's say that you have extracted some particles, you have aligned them to a 3D class, you have separated into different 3D classes, and then for a particular 3D class you want to see how these subtomograms look like into the original tomogram. So now you know where each cube was coming from, you know the transformation, and you know the 3D class. So now you can be very flexible. So you can take, for instance, the 3D class and put it back into the tomogram, or you may highlight in the original tomogram the cubes that are coming from this 3D class, or you can erase those areas, or you can binarize those areas. So that there are a lot of possibilities there to highlight a particular 3D class into the original tomogram. Then we have a very good connection personally to the person of Dynamo, and also at the level of programs we have integrated many of the steps that you can do in Dynamo, and we are growing in that direction, and that is one of the active areas currently in the lab. So you may do whatever processing in Dynamo that you like, and then at some point you may export the table of Dynamo, the Dynamo table is somehow equivalent to our metadata tables, and there you would have what is the subtomogram and all the information that Dynamo keeps for that subtomogram, including the transformation matrix, so that you can apply, so you can calculate the transformation matrices in Dynamo and then go into Scipion and apply those transformation matrices to have the same average that Dynamo has computed. Then we are also calling the Dynamo tools for defining regions. So regions of interest in Dynamo, they are called models, and then you may define your models based on a geometric description like an ellipsoid or a surface, or you may also define them just by clicking points, and then the points will be connected into another surface. And we have also connected or we are in the process of connecting the regions of interest defined in Scipion and being able to see them as in the Dynamo viewer. And these models help you to do something that is very interesting, that is vectorial picking. So vectorial picking is, let's say that this is a surface, this is a membrane, and you have a protein here in this membrane. So when you pick your particle and you say that this is a particle, you don't not only have the location of that particle, but you also have what was the surface at that point. And then if that protein is facing outwards the membrane, you have what was the surface, so that you can define directions, and you can define the perpendicular to the membrane, for instance. And when you extract, you keep that orientation of the membrane, so that you can automatically have an estimate of what is the transformation matrix to have all the subtomograms aligned, for instance, with the vertical direction. And the vectorial picking, again, this is in progress. This was taken from the ERC presentation, but now it is fully finished. And the Dynamo extraction with the orientation, it is also done. Then we call Dynamo for 3D classification, and 3D classification in Dynamo has several flavors. So one is a single reference, so you can align everything to a single reference and have all your particles aligned. Or you may do a 3D classification, and the 3D classification has a principal component analysis or a multi-reference alignment. And we are able to call all of them, take the output of all of them, and transform and understand the transformation matrices, so that if now you go into another program, you can apply them and have the particles aligned as Dynamo predicted. Then one of those programs for classification is this maximum likelihood tomography alignment that we had in XMIP2. For some reason it doesn't work so well in XMIP3, but the nice thing of Scipion is that it integrates plugins based on different software packages, and XMIP2 and XMIP3 can be treated as different packages. And so we take a set of subtomograms, submit it for MLTomo, and MLTomo will do a 3D classification of those subtomograms. So the future work is improving the integration with Dynamo. Dynamo is a very rich package, so we would like to have more operations that are defined in Dynamo. Then we are now working on the integration of the subtomogram averaging protocols of Relion. Also the subtomogram averaging, especially the multi-reference alignment of Iman. And then what is in the pipeline is the integration of PySeg. So PySeg at the moment we haven't started to integrate it into Scipion, but it is already in the pipeline. So as long as we have a free resource, a free person, he will integrate this PySeg. And So in conclusions, so having this tool of everything integrated in a single platform is not only very convenient. You can go from one package to the other in a very easy way, but it also adds a lot of scientific value because you can define better workflows. So if you know that for this particular data set or for this particular kind of data, Dynamo does this operation very well, and then XMIP does this operation very well, and we can denoise with this other tool. This will result into much better imaging than just being constrained to a single tool. And the other one is that you can now start to define consensus. And for instance, you may perform a 3D classification using Dynamo, a 3D classification using Eman or Relion, and only believe those classes that share a lot of supporting particles. So all these classifications, they all have a lot of false positives. So classes often get particles that really do not belong to the class. So by comparing the classification results from several programs, you are able to be more sure about your statements of what are the different classes that you have in your structure, in your tomograms. And this is the work of many people in the lab, and especially those more related to tomography are Estrella, Federico, David Herreros, Adrian. Adrian has been invited to the talk, and Pablo, Ana, Javi, Jorge. So there are many people working on this. Actually, I'm the only one who doesn't work on it. It is the work of many other people, not me. But I somehow supervise all of them, give ideas, but I don't program anymore in this area. So if you have any question, I'll be glad to answer.